with that. So, yeah. Oh, you got to be in polar mode, right? So on your calculator, go to mode, and then you can see like there's rec, par, pol, sec. You want to go to POL, and you go R is equal to 2 sine of 3 theta.
Where's theta?
It's your xt theta n. So when you're in polar mode, that just shows up as a theta. Just like a t when you're in parametric.
Did you know Leibniz was like a big philosopher?
Yeah.
Yeah, they learned about him in senior biology.
We learned about him yesterday.
I remember.
So those guys of the past, like the Leibniz and Descartes and all these mathematicians we know about, they were like the rock star philosophers too. So
I got this whole thing about like the universe and how it's created, or I don't know, don't even know.
Where did we learn Leibniz in calculus?
So
It's
dy
dy
dx is Leibniz's notation. That's exactly right.
That's right.
And so those guys were like the professional athletes and rock stars of their time. They were like popular and smart and looked up to. So, okay, are you guys getting a nice, happy rose for this one? I'll try to sketch this out. Is it? It's. Is it this one? That's a little lopsided, but is that the one, or is it? The single one is going down. Okay, cool. Thank you. Okay. So there's an example of what that looks like. You all see it on your calculator. But what I would like to do is take a second and plot this out and talk about what's actually happening. The equation here is r is equal to 2 sine of 3 theta. And so we could actually plot this out by plotting some points. The points we'd be plotting would be based on theta and r, of course, not y and x. And so let's plot a few of these out. We don't have to do every single one of them, all of the unit circle ones, but let's do enough of them where you can get a sense of the shape and see how it works, talk about what's actually happening, and we'll go from there. So what would be a logical theta for us to start off with?
0.
0, always a good one to start off with. So if I plug in a 0, I get sine of 0.
Which is 0.
Well, sine of 0, 0 times 2 is 0. Okay, so when we are pointed straight right, the radius is 0. It's really important for us to understand what those two things mean. So when you're pointed straight to the right, the radius is 0, so nothing really shows up. We're still right there at the origin. The next logical one I'd say would probably be pi over 6, as far as an angle that we know something about. So if you plug a pi over 6 in there, of course the 3 and the 6 do some canceling out. You end up with sine of pi over 2. Pi over 2. And sine of pi over 2 is
1
times 2. 2. Okay. Next one maybe would be pi over 4. So if you plug in a pi over 4, you get sine of 3 pi over 4. And this is where it gets a little weird. Maybe we use the calculator to get an approximation so we can plot this. But sine of 3 pi over 4 would be that root 2 over 2. Multiply that by 2. You just get root 2. Do you guys know what root 2 is, roughly?
1.414.
Yeah, 1.414. Very good. Okay. So that means when you're pointed at kind of a 45-degree angle, a pi over 4 angle, kind of up and right, the radius is only 1.4 approximately. So as you can see, what's really happening here is as the angle changes, as you go from 0 to pi over 6 to pi over 4, as we do that, the radius is getting longer or shorter, right? It's just lengthening out or shortening up a little bit. Another good one here would be pi over 3. If I plug a pi over 3 in there, of course the 3's cancel, you get sine of pi, which is 0. Yeah. And times 2 is still 0. And maybe we do, no, let's leave it at that. Let's leave it at that for now. Let me go up here and plot this. So the first point is when we're pointed straight right, the radius is 0. So that just puts us right there at the origin or the pole. When you're pointed at pi over 6, the radius is 2. So I would say, we're pointed, pi over 6 is like right about there. So we're going to go out a distance of 2. So there's that point. Pi over 4 is 1.414. So that's that 45-degree angle. This would be like right about here in the middle, somewhere as far as the 1.4. It'd be halfway between the 1 and the 2, roughly. And then we get back around to pi over 3, and we're back to the origin, right? So as you start to trace this out, maybe you can see that this is one part of the rose, isn't it? So as we travel along here, you can see that this would do something like this. You know what? Let me use a different color. The rose, let's make it red. Like that. And then this piece would be this travel, right? So, we've done this in very choppy fashion because we only have these unit circle angles to do without the calculator. But we've plotted out kind of that first petal of the rose. Let's do it just a little bit more here. If I kept on going beyond pi over 3, what would be the next logical unit circle angle? Pi over 2, yeah. So if I go with pi over 2, you plug in the pi over 2, you get sine of 3 pi over 2, and what's that? Yeah, -1 times 2, -2. Okay, well, so that's kind of interesting. So when you are pointed straight up, you actually walk backwards, right? So when you're pointed straight up, you're going to go back down backwards to the bottom of the graph, which is right there. And as you remember from what you saw in the calculator, wouldn't this be kind of like the bottom part of that lower petal? And so this part, we're missing a lot of the stuff in between. This part would go down through here, come on, to here. And then, of course, you could plot some of those second quadrant angles, and you'd find that this, continues to be developed here, and eventually you'd get around to here and plot out and finish that last petal. So all that's really happening here is as you rotate around the graph here, the radius is changing lengths, and as it gets longer, you're going to get out towards the end of a petal. As it gets shorter, you're going to get closer, and so on and so forth. I thought I would do one more thing here with you guys, and we'll move on to the other graphs. And I want to do this on my calculator, and maybe you guys could do the same thing here with me. So bear with me for 1 second. I want to talk a little bit about what is happening here and talk about some domain ideas. Yeah, go ahead.
My calculator, when I plug in pi over 4 for theta, it gives me 1 instead of 1.414.
Well, let's see here. Hang on. Something that maybe you've already done this, I don't know. But I thought I would show you something to kind of help you understand what is happening here. Let's go polar. And I'm going to put this in there. 2 sine of 3 theta, right? 2 sine of 3 theta. And would you guys do this with me? You already have that in there. Would you guys go to your R2? And for your R2, will you please just go 2? So 2 sine of 3 theta. R2 is 2. And now go back to mode. And you can see my screen up there? On mode, I want you to scroll down. Do you see sequential is blinking? Don't do sequential. Let's do simultaneous. So hit simultaneous. Switch it over to that. And then as far as window goes, was a Zoom 6 working for you guys? Or maybe smaller than that. Let's go to window. And let's go plus or minus 3s. That makes sense. Okay, so x min, -3, x max 3, and then -3 to 3. So maybe watch it on mine, and you can watch it on yours too. These are going to graph simultaneously. And what is r of 2 equals 2? Like, what will that be on a graph?
Circle.
It's a circle. So check out what happens here. So you graph it. You notice anything unique there? It kind of was going fast. Let me do this. And clearly you can see it's a circle. I'm going to slow theta down a little bit. I'm going to go like 0.6 0.07, maybe, something like that. And watch it carefully. Can you describe something unique, something that jumps out to you?
Are we looking at the red or both?
Both. You're looking about the relationship between the red and the blue. Let me do another one. Yeah, so I'll slow it down a little bit more for you. 0.05. So it'll be a little slower. So careful. You need to watch. You can't just watch the result. You need to watch the process. So watch what's happening.
Oh, they hit at the same time.
For the positive, on the positive Y,
Check this out. Maybe
positive.
this might be interesting. What if I change this to our friend the beach ball? This might be even better. So let's graph this. So if I graph this, you can see the rose getting traced. And right about here, the rose is done.
Keeps going.
How many times did the rose get traced?
Twice.
Two whole, no, I'd say 2 whole times, wouldn't you? Check it out. How about, we'll slow it down a little more. 0.04. So here's a graph. So there's 1/3 of the rose, 2/3 of the rose. At this point right here, the rose is done. There's 1 time. Do you see it's going through that second time now?
5/3. What?
2 whole times, right? And so in the time that it took that circle to get formed, the rose got traced 2 whole times. So what does that tell you about the domain for the rose? What should it be?
Limited
To what? I agree, limited.
to how long it takes just to go dot once.
And how long do you think that would be? Pi. So check this out. What if I went back to my window and I changed my theta min from 0 to 2 pi? I changed it from that to theta to pi. Right? So I just took half of the domain that I had before. So if I graph this, watch what happens. The circle is doing its thing. There's the rose. La, 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 la. The rose has not been traced yet, but now it has, and it stops, right? Because I limited the domain for both. You can see that all it takes is 0 to pi. Can you see that on the red? If the angle goes from 0 to pi, you get this rose here. And if you went 0 to 2 pi, you'd get the rose traced twice. If you went 0 to 3 pi, you'd get the rose traced 3 times, et cetera, et cetera. That makes sense? So we're kind of exploring a little bit about the domain. You can kind of see it being formed, the radius going from short to long to short, so on and so forth, forming this rose. Make sense? Okay. So let's do a little bit more of this. Let me get out of this screen. Yeah, let's, if you would, on your calculators, take a look at the middle one, 3 cosine of 2 theta. 3 cosine of 2 theta. Should be another beautiful flower, rose. See what it looks like. We'll do some messing around with it again like we did with
What
that.
does
And
that
you,
mode do? The mode where you switch to.
so simultaneous, that means if you have more than one equation entered, it'll graph them at the same time. If you're on sequential, if you have more than one equation entered in there, it'll graph one, then the other, then the other.
Okay.
So, and both of them have their purpose.
Maya did sign it first. It doesn't look like a butterfly if you turn it like this. If you twist it like this, he's kind of a
So this was a bit of a bigger rose, right? Oh man, mine's lopsided, sorry. I did my best. It is kind of a 4-leaf clover. There, let's call it a clover. So did you guys get that?
Sure did.
So you start to look at this and you realize, there's some interesting things going on. For instance, if you think back to the one we just did, there were some interesting patterns that perhaps arose. Did you notice that? I just got that too. That was pretty good. Did you guys notice that the 3 on the input, I'm referring to the previous one, right? Did you notice that the 3 on the input matched the number of petals? But then when you look at the one we just did, the number of petals was double the 2, right? Like, is there a pattern there, that kind of thing? I don't know, maybe you noticed some interesting things in regard to, did anybody investigate the domain like we did with that other one?
This one we're doing is 2 pi.
Yeah, this one, the domain needs to be the full 2 pi. So if you did the same kind of thing over here, if I change this over to 3 cosine 2 pi like we're doing, remember my domain right now is just 0 to pi. So if I were to graph this,
You want to make it 3.
Can you figure out the domain?
look what happens. By the time the red circle just goes 0 to pi, I only have half of the rows, right? I only have half of it. If I want the full rows, like Blake suggested, we need to go 2 pi with our domain. So there's that. So we graph. Now you can see the red circles being formed. Here is our 4-leaf clover. It's halfway done. The circle is halfway done. As the circle finishes, the whole 4-leaf clover thing finishes also. Okay, besides the beautiful artwork, a little pattern is emerging here a little bit, right? We're going to do one more and try to discern a little more of a pattern. Of course, if you made your domain bigger, the flower would just get traced more. Is this making sense? We still okay with the idea that as the angle changes, the radius changes length as well. So as you rotate around the graph, the radius is going to get longer or shorter, depending on the relationship between r and theta. And that's what forms these graphs. McKenna, question? Possibly?
Does the number in front, so it's like 3 cosine 2 pi,
Yeah.
does that number like represent like the max?
Yeah, with these roses, yeah, maybe you notice so this was a 3 cosine 2 theta, and you can see that the longest the flower petals get is 3. So yeah, there is a relationship there. You bet. And the other one was 2 sine of 3 theta, and so then that max length was just 2. So it's a little bit of a smaller rose. Okay, so then what's the last one? Is it? Yeah, so 2 sine of 5 theta. Use your calculators again and check this out. And maybe you'll notice similar pattern emerging. So 2 sine of 5 theta. So when you graph this one,
Remember last year we learned about like where they start to?
I didn't learn that last year.
Oh wait, you went from the last year.
No,
Oh, you went just.
Yeah, I was learning all that.
did you guys notice here that the domain is back to pi?
Science.
Patrick Star.
Okay, can we test out your theory? Check this out. Did you guys hear Lenny's theory? Lenny said when it's sine, the domain is pi. When it's cosine, the domain is 2 pi, right? So let's check this out. What if I change this a little bit? What if I made this a 4?
It would be 8 petals.
Oh wait, it's even odd.
It's even odd. That's right. It's not about cosine and sine. It's about even and odd. So of course this does have 8 petals, but that's really nice. Yes, I agree. And I did that all by myself with my calculator. So, anyway, so it is more about the even or oddness of that coefficient on the input, right? So the domain is going to be affected by that. The length of the petals is what McKenna was mentioning. So that coefficient out front is going to affect that. So let's see here. Let me point out a couple of other things. Can I point out to you guys? I'd like to point this out to you. It's a little foreshadowing. Can I explain why it's so important for us to understand how the domain works with these?
Yeah.
It's really important for us to understand how that works. And let me slow this way down a little bit here so I can kind of talk while it's doing its thing. Something like this. So guys, listen and watch. One of the things we're going to do with graphs like this is we are going to find, Blake, you want to watch? We're going to be finding the area within certain segments of these graphs. And the way that we're going to find area is not with rectangles that we accumulate. We're actually going to sweep out area with sectors. Do you guys remember sectors? It's like a little segment of like a circular curve region. We'll talk about this a lot more later. But listen, so if I was going to find the area of the petals of this flower, you can see what I'm doing here is I'd be sweeping out the area. I could sweep out the area of one of those petals. And then I'd get the area of another petal right there, so on and so forth. You can see we're just progressing nice and slow. At this point, if I accumulate all this, I'd have 3 petals, right? So I'd have some of it, wouldn't have all of it. You can see at this point, I'm back to the 5-petaled flower, 5-petaled rose. At this point, right about here when we get to pi, if I stopped integrating, wouldn't I have the full area of all the petals? If I messed up my domain and I retrace this, wouldn't I have twice as much area as I should? Because if I told my integral to go from 0 to 2 pi, it's going to say, all right, and it's just going to keep adding up, even though I only needed 1 pi to get the full area. If I keep going, it'll just keep adding them up, and my area would end up being 2 times too big. So it's really important that we're able to discern, well, you know what, to cover this amount, we only need this domain. To cover the whole rose or half the rose or just one of the petals of the rose, we need to understand what domain would define whatever it is that we're trying to figure out. So, an example question would be, I could give you a graph like this, give you the equation and say, what is the area of one of the petals of this rose? And if you're able to decide, okay, here's how I would get one of the petals by defining my angles correctly, then it would be no problem. But if you're like, well, I got no idea how to figure out the domain of something like this, it's going to be hard for you to figure out your alpha and your beta limits for the integral. Like I said, you don't have to remember any of this because we're going to do this a lot later, but this is one of the reasons why we would say, why we care about the domain. McKenna, your question.
This is probably stupid, but
Oh, don't start like that.
the areas of each petal are different.
No. So there would be a multitude of ways you could do this. So one of the ways, like if that were the question, find the petals, one of the petals' areas. Couldn't you find the area of all the petals together and just divide by 5?
So they're all the same.
Yeah, there is symmetry here. Yeah.
Gotcha.
It's possible to have all kinds of crazy graphs that don't have symmetry, but one of these roses, yeah, they're all the same symmetry. Yeah.
Since it's polar, does the whole above the x-axis is positive and below is negative stick out or no?
No, yeah, well, don't worry too much about that stuff. We'll get into that. You're going to find that the radius gets squared in the process of this formula. And so whether we're talking about a positive radius or a negative radius, it's not going to matter because it'll get squared. Yeah. Good question.
Is it too late to draw?
Okay.
What's the exact rule for these odd?
Yeah, let's talk about that right now. Yeah, so let's formalize this as far as the patterns here. You know what? I'll just write this down below. So here it is. If we have, we'll just try to make this as general as we can. If we have R equals A cosine of B theta or A sine of B theta. So these would be examples of roses, right? A cosine of B theta or A sine of B theta. So what A is going to do? A is going to tell you like the max petal size. So if A is 10, then the furthest away you're going to get from the origin is 10. If A is 20, then the max distance would be 20. And then B, so B has a little bit more here. And I've kind of, like there's some of this stuff on the other page. If you look over here, I put it on that spot, but we can do it right here as well. So B, if B is odd, then your domain will just be just a single pi, right? So I'm going to say your domain is 0 to pi. Does that make sense from the pattern we saw? And then there's one more connection we can make. If B is odd, the domain is 0 to pi, and the number of petals is what?
It's the same.
Yeah, it's B. So if B is odd, then there will be b petals, and your domain is just going to be pi. And when I say pi, it could be negative pi to 0, it could be negative pi over 2 to pi over 2. It just needs to be a distance of pi. We probably would write 0 to pi. That'd be a typical way of doing it, but could be anything as long as the distance is pi. So then the other, of course, is if b is even, then your domain doubles, so it'd be 0 to 2 pi. And the number of petals would be what? 2b. 2b, you are correct. Okay, so these are just, like, these roses come up pretty often, and so these principles apply to roses, right? So let's not take this and run too far with it. Okay, these principles apply to roses only, and roses are very common, and so I think it's worth talking about these a little bit. Okay. Any questions? So, McKenna, there's some addition taking place, and addition's going to do some different things to these. And then the one on the far right is its own unique thing, and we'll take a look at that one as well. So why don't you just graph the one on the left? R is equal to 1 plus 2 cosine theta. And for those of you that had polar graphing before, we're going to be looking at limesons, looped limesons, and then also cardioids. Those are three. These are all three related things: limesons, looped limesons, and cardioids. And we're going to talk about a lemniscate after that. Infinity, right? Yeah. Or a vertical infinity.
Yep.
Yeah. Like an 8.
Like I have those ones down.
Good.
I don't like these guys. These ones are hard. They just like are hard. The shape makes me uncomfortable. I just don't enjoy them.
Yeah, there's the limason, the dimpled limason, the looped limason, and the cardioid.
This is a loop limason.
Okay, so this one has a loop, doesn't it? The one on the first one here. And it's cosine, so it's got to open horizontally. So let's see here. Oh boy. These are hard to draw. I might have to do some restarts. Oh. Whoa, I hope, I get that oriented right? That's one of my better looped limesons I've ever drawn. I'm quite pleased with that. Maybe that could be my conservatory thing. What jury?
Yeah.
I could draw a looped limason.
Great.
And then be like, you are the best looped limason drawer. You're in. You're still in. All right. Okay. So guys, this is, of course, the same concept as what we were doing before, where the radius and the length of that radial line depends on theta, right? So as theta sweeps out, from 0, and we needed 2 pi for this, right? Did you guys see that on the calculator?
Yep.
Maybe you did. You had to have 2 pi for this. If you only did 0 to pi, you'd only get half of it. And so there's some interesting things that happen here. For instance, I would look at this little inner loop right there and say, man, where did that come from? Like, why does it kind of double back on itself and form this little loop? Like, what's going on there?
A 1.
What do you mean a 1?
Cosine of pi.
I don't know.
Okay, so cosine of pi. Yeah, so you know what? That might be a pretty good thing to plot, because pi, of course, is when we are facing straight left. So what's going on when we're facing straight left? It looks like we're going backwards, right? Instead of going to the left, which is the direction we're facing, we're going right. So if we plotted that out real quick and we said theta and r, and McKenna suggested pi, if you plot that, you get 1 plus 2 cosine of pi. Cosine of pi is -1. 1 plus -2 is -1. So that's where at least one of the points on that little inner loop comes from. You'd say, okay, so if we're facing left, we're actually plotting a point off to the right. That means we have to be facing left and walking backwards. And you can see that all of these points, like for instance, let me change colors here. Like this point here and this point here, all these yellow points, all of these are actually formed by facing into the second and third quadrants, right? You're facing into the second and third and then going backwards. That's where that little inner loop comes from. Couple of other thoughts. You can obviously see that from an XY perspective, this graph radically fails the vertical line test, right? So y is not a function of x. This is not your classic function where you could do the vertical line test and see that. R is a function of theta. It does not mean that y is necessarily a function of x. Lastly, I'll point this out here. Let me give you just a preview of some of the stuff we'll do with calculus with this. You could get some graph like this, an equation like this, and the question you might be asked is, find theta when you have a horizontal tangent line. Find theta for the places, find the thetas where you have a horizontal tangent line. So if you look at the graph, when you see a graph, you can actually see these relatively easily. How many horizontal tangent lines do you think this would have?
2.
He says 2,
Wait,
4.
4.
Anybody want to go for 6 or 8?
I think it's 4.
So there's one right there, and there's another one right there, and then doesn't that little guy on the inside have some? Yeah. One right there, one right there. So I think there would be 4 different angles where you've got horizontal tangent lines. Another thing that you could be asked is, what if it said vertical instead of horizontal? How many vertical tangent lines do you see?
4.
There's a pretty obvious one over here on the right.
2.
And there's another one right here.
I think that third one covered.
So it depends on how the question's worded, right? If I said find all the thetas where you have vertical tangent lines, wouldn't there be 2 additional ones? There'd be 2 additional thetas. There'd be one right there. There'd be another one right there. But I think you can kind of see based on symmetry, wouldn't those 2 different lines actually be the same line? And so if I said, what are the equations of the tangent lines? I think we'd only have 3 equations of tangent lines, but there'd be 4 different thetas that would produce them. So those would be some things you could also see. And then, really, honestly, another question I could ask is, say, what is the slope of the tangent line when theta equals pi over 3, something like that? So what you would do there is you would say, all right, you'd need to know how to find the slope of the tangent line first. But then you'd say, all right, well, when theta equals pi over 3, which, I don't know, is like up there somewhere, maybe that would be where you'd have a horizontal tangent line. Or maybe it would be when you're at pi over 6, you could find the slope of the tangent line. That'd be maybe a negative slope over there. So what I want to help you understand is that all this stuff is still the same stuff, right? The slope of the tangent line is still dy dx. The tangent line is still the tangent line. It hasn't changed. We just have different parameters than we normally do. We have r's and thetas that relate the x's and y's instead of just x's and y's.
DRD theta.
DRD theta has its own meaning. For instance, hey, check this out. What if I gave you this question here and I said, find DRD theta, and maybe you found it? I might ask you to interpret it. So what would you say if you calculated DRD theta, and what if DRD theta was like -1? What do you think that means if DRD theta was -1? Change in r with respect to theta is negative, but what does that mean, though, in terms of the graph?
That is positive.
Going backwards.
That's in the
Wait,
first
that
2
is-
quadrants.
That is theta increasing.
If DRD theta was -1, I'm just making it up, what do you think that would mean? Think about what r means, think about what theta means. I'll start you off. If DRD theta was -1, you could say when we're at theta, whatever that angle is, the radius is, the radius is not -1. The rate of change of the radius is -1. So that means the radius is
Decreasing.
getting shorter, decreasing. Right? So, and this is another principle, and you said it right, decreasing. That works. Decreasing could be a little ambiguous, but I would take it, I think. Getting shorter, remember one of the ends of the radius is always on the origin, right? And the other end is either getting further away or closer. So if DRD theta was -1, then you would say we're getting closer to the origin, or the graph is getting closer to the origin. All kinds of different things we could ask here. So consider, if you keep in mind what r and theta and x and y are and how they're different and how they're related, should be okay. Okay, would you guys take a look at the next one? R equals 2 plus 2 sine of theta. 2 plus 2 sine of theta. So sine tells me it's going to kind of be like up and down a little bit instead of left and right.
Is it positive sign goes up, negative sign goes down? Like if it was 2 minus?
Let's see here.
Right and left for cosine?
Well, yeah, so cosine is going to be kind of like a left-right thing with these. Sine will be an up-down, but you're talking about like, because this is a cardioid, right?
Right.
Like how could you reflect it down?
Right. Wouldn't it be 2 minus 2?
I think if you just had, I think if you did negative 2 minus 2 sine theta, you just multiply the whole thing through by a negative.
Or is this 2 minus 2?
Is
I
that?
always thought it was just the whatever the coefficient of the sine was.
I honestly don't remember how to transform that. It could be, play around with it a little bit. So this is actually a little bit too big for my graph, isn't it?
Yeah, I know, it's random phone.
There. He's kind of upsetting. It's a lot cuter than mine.
Oh boy.
Mine has some surgery for flowers. Yeah, me too. Can we go back to flowers?
Yeah. Man, I'm struggling. That's the best one I got right there. Do you guys get a cardioid like that? Upside down apple. Of course, cardioid, heart, is it a little wider? Oh man, okay, I'll give this one more try hopefully.
Are you sure of that?
You add the coefficient.
No, you were right. You were right the first time.
Okay, because I knew it went up to 4. I know it peaked at 4.
I was just reading the graph wrong. No,
Hey, there we go, that's better. Okay, so you guys notice a couple things about this, this cardioid. You needed the full 0 to 2 pi to get it, right? 0 to pi would only give you half of it. So, you know, a trend here, like so the looped lemmason, the dimpled lemmason, and the cardioid. We didn't do the dimpled one. Just has to do with the ratio of the A and the B here, the 1 and the 2 or the 2 and the 2. So like if it was 3 plus 2 sine of theta, we start to just see a little dimple appear as opposed to the full cardioid. In any case, are you noticing that these cardioids, lemmasons, looped lemmasons, dimpled lemmasons, they all need the full 0 to 2 pi, right? You can't get these with just 0 to pi. Same kind of thing here as far as what could be asked. How many vertical tangent lines, how many horizontal tangent lines do we have going on? What might be a unique question that I could ask you about this one that we're on right now? What is a unique feature of this one as compared to the looped one we just did? Yeah, you could, you know what, I hadn't thought about that, but yeah, you could ask this question. You could say, what's the area below the x-axis, right? This would be, like a question like that would take a pretty good amount of space and time. It wouldn't be that bad. I don't know. Maybe I should go throw that on a quiz or test right now. I'm kidding. I'm just messing around. The quiz has been written for a long time. Yeah, I like the quiz already. It's okay. Come on. What is one feature of this graph that this graph has that none of the other ones have had so far?
No loop.
No loop. Oh, you could say the whole thing is a loop, though.
And there's only one loop.
There's only one loop. Okay, I'll give you that. What else?
Doesn't intersect at something.
True. What else?
It's facing up.
Yeah, but so did the clover. The clover kind of had a facing up loop. Something really unique about this one that none of the other graphs have had.
It's a heart.
It looks like a heart.
And a heart has what?
A point.
Two
A
halves.
point.
Oh.
Do you see it right there?
Yeah.
Doesn't a cardioid have a point of non-differentiability? It's got that sharp point right there.
Doesn't the one that you also have that point, but it also makes a loop before it?
Wait,
No, no, because it's just retracing over itself.
What did that guy say on that test? That was like.
Oh, the doink point?
doink.
Doink point, yes, the doink point. Yes, it's a doink point on the cardioid, yes. I had forgotten about that. Thanks for reminding me. Okay, so that's a cardioid. And like I said, if you guys want to mess around with this for a second, if you had something like r equals 3 plus 2 sine theta, I think that you would see the sharp point go away. It would become just what's called a dimpled limacon. And you could almost think of this, there's a relationship between the looped limacon, the cardioid, and the dimpled limacon. Somebody, it's been many, many years, but somebody brought up the idea that it's almost like evolution, like something disappearing or whatever. Like the loop limacon, it's got a loop. And then the cardioid, the loop has disappeared, but there's still a sharp point there. And then the dimpled limacon, the sharp point is kind of smoothing out a little. You get what I'm saying. Kind of silly, but whatever. And then, of course, if you just had 2 sine theta, I think it's just a circle. So I don't know. Whatever. Last thing here is the lemniscate. Lemniscate on the right there. Take a minute. Let's take a minute and investigate this a little bit. You notice it's r squared, right? It's r squared. So if you're going to put this into your calculator, you're going to have to square root both sides, aren't you? So, and you got to have plus or minus. So you're going to have r is equal to plus or minus square root of 9 cosine of 2 theta. Take a minute, graph that. And I think this should look like an infinity symbol. Right? The sideways 8. If you have your theta step small enough, go back to your window. Make your theta step like 0.01 or something. And then you probably, and then just hit graph. It should connect. It's going to be slow, but it should connect.
True.
So the lemniscate forms like this.
Mine still leaves a space by the origin. Is that just like a
We just got to tighten it up a little bit more. Have you guys noticed the way that it's formed? Did you pay attention to the ordering of like how the graph appears, not just the finished product, but like how the little points are actually getting laid down? I think if you graph r equals positive root 9 cosine 2 theta, you get that part first. Does that make sense? Domain, play around with the domain, 0 to pi, 0 to 2 pi. I think you only need pi. I think pi is all you really need.
No, you just put a second one in the second.
How do you make it regraph? You have to like change something.
Yeah, go to window and maybe change your theta step to like 0.06 or something. And then you can rewatch. Just hit graph now.
I see it goes up.
Yeah.
For me, it doesn't.
Yeah, the upper half. Yeah.
Yeah. 0.131.
So some interesting stuff happens here, no doubt. If we plot a couple of points, we can talk a little bit about this. Maybe we'll return back to the calculator. If you've got theta and you've got r here on this one, an obvious theta would be 0. If you plug in a 0, you get cosine of 0, which is 1 times 9 is 9. And square root of 9 is 3. If you think of it as plus or minus, don't you get plus or minus 3? So what's unique about this is that when theta is 0, you got to put a point out to the right and a point to the left, right? So you'd I don't know, let me go back and just restart this. So 0 plus or minus 3, so if I'm facing right, I've got to put a point out here and a point over here. Does that make sense? Maybe we try, I think pi over 6 will work out okay. So if we try pi over 6, what would be cosine of pi over 3? And cosine of pi over 3 is, that's 1/2, isn't it? So it'd be the square root of 4.5, which is like 2.2-ish. But it'd be plus or minus, wouldn't it? So plus or minus, I'm estimating about 2.2. So when you are facing pi over 6, you're going to be here and here. So do you see how it's laying down kind of both halves at the same time? And so once you get up to a certain amount, let's see here, I think we go one more here. Pi over 4. If you plug in a pi over 4, you get cosine of pi over 2, which is 0, times 9 is 0. You're back to 0 there. So this would give you that point right there. And so at this point, you'd have this right here, roughly. And there's going to be a stretch in the middle where the domain doesn't work at all, does it? I don't know if you noticed that or not. We might be able to explore the calculator a little bit. Once you get above pi over 4, say pi over 3. If you go pi over 3, you go cosine of 2 pi over 3. So cosine of 2 pi over 3 would be negative 1/2, wouldn't it? No, it'd be negative root 3 over 2. No.
No, negative 1/2.
Negative 1/2. Negative 1/2 times 9 is negative 4.5, but the point is it's negative. And we're about to do the square root. That means there is no real number that goes with that. So you're going to find that between pi over 4 and 3 pi over 4, nothing happens. So from, I'll just put it like this. So from pi over 4 to 3 pi over 4, it's like this space in here, dne. So the graph would just sit there the whole time. And then once you get from 3 pi over 4 and above to pi, you start to get actual outputs again. And that's where the other part of the graph comes from. So lemniscates are super unique because you get part of it, and then it just sits there and does nothing for a while, and then you get the other part of it. So you guys can all probably see the opportunity to ask for area. Is there, right? Like what's the area within the lemniscate? What are the equations of the horizontal tangent lines, equations of the vertical tangent lines? All those sorts of questions would potentially be in play because we're talking about the same sort of stuff. Okay. We've looked at a lot with polar stuff. Do you guys have any questions? Just what ifs? I might be able to answer them. Some of the what ifs can get kind of out there. I might or may not have a good answer for you right now. McKenna, yours.
Do you know the names of those things?
Yeah, great question. I think that that's helpful, but I would never quiz you. I would never say, here's an equation and here's a graph, name it.
Okay, cool.
But I might say something like the equation of a lemniscate is blah, blah, blah. And if you could think to yourself, lemniscate, oh yeah, that's the infinity thing, or the, if in the lemniscate here, if you replace the cosine with a sine, it would actually, instead of looking like an infinity, it'd look like an 8.
Mm-hmm.
So, if you could start to associate some of these like names with what the graphs look like, I think that would be really helpful because you could think, okay, a lemniscate, okay, you could have horizontal tangent lines, here and here. If I said, hey, the cardioid has this equation, you'd be like, oh yeah, the cardioid, that's the one that could have the sharp point. Things like that could be helpful, but it's not like if you didn't know those or couldn't associate those, you have no hope. You could still do it.
So what are the names again?
Okay, so yeah, so this right here, so you know what, I should have written those down. So this is a lemniscate. Lemniscate, I think, has a C in there. This is a cardioid. This one over here is a looped. Limousin, and the C in Limousin has like a funky,
Limousin.
I can't remember, is it below or above?
It's below.
Below, yeah, I knew there's like some little mark there. Limousin. The other ones are just called roses. I mean, those are easier to remember. Yeah. Other questions? I've tried to also give you sort of a preview of what we might do with this stuff in regard to calculus, its area, and dy dx. It's not surprising. The last thing I'd encourage you to do here, I'll give you a preview of some of the calculus stuff in our last 5 minutes. The last thing I would encourage you to do, and if you have time to do it, do it. I know we've got a quiz tomorrow over vectors. But over the weekend or whatever, if you're like, oh yeah, that polar stuff, if you just want to mess around and just see what happens, sometimes I think that's the best way of learning. Is like, what if? What if I added an x to this? Or what if I subtracted a theta from that? Or whatever it might be. I think you might find some interesting
You want to see what happens when you make your theta step 10,000?
X and theta. This is one of those relationships we looked at earlier. X is equal to r cosine theta. And y is equal to r sine theta. Does that make sense? So what I'm going to do here is I'm going to take you through a little formula that will help us remember. But we're going to kind of recreate this formula each time based on the custom situation we're in. I'm going to remind you parametrically. Well, let me just take you back to what we did with parametrics. Do you guys remember with parametric and vectors, dy dx is equal to dy dt over dx dt? So same kind of relationship here. In regard to polar, dy dx is equal to dy d theta over dx d theta. Very similar relationship. It's just that theta is going to be our parameter as opposed to t, time. So let's keep in mind one thing here as I show you this. Think back to all the graphs we've done, and you can look back on all the graphs we've done, especially of all the curvy ones. On all of those, wasn't r dependent upon theta? Like it was r equals 2 sine of 3 theta. R equals blah, 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 something or other theta. So let's keep in mind that these two right here, these are in terms of theta. And if those two r's are in terms of theta, then here's how this would work. If I was going to do dy dx, and I'm going to find dy d theta, isn't y a product? Okay, let me go back. Looking at this, do you see how y is the product of r times sine theta? Lenny, what are you doing? Okay. You're totally welcome to do that. Like I said, we'll practice this a lot, and you'll kind of probably get a sense of it and kind of have it memorized just naturally. So anyway, quiz on vectors tomorrow. We'll pick this back up on Monday. McKenna, your question?
Wait, is r a constant?
Nope. So think back to all the graphs we did. Weren't all of them things like r equals 3 plus 2 sine theta?
Okay.
Or r equals cosine of 5 theta, or whatever it might be. And so this would just be in place of the r's.
I was just seeing like the R is the 2 and that equation.
Oh, sure. Yeah. No, r would be a whole different function in terms of theta. Yep. Don't worry. We'll practice it a lot. I'm not expecting you to have this mastered right now. I just wanted to kind of show you what we'll do, and we'll come back around to it.
Are we gonna have